It's a good idea to have some water ready to go.
Yeah.
Yeah, like so everything's working.
Do you have any recommendation for a speech recognition program that runs locally on a machine rather than in the cloud, other than trying to actually speak?
I don't actually know. So.
TensorFlow is suitable for general purpose.
Yeah, it should be. If you have something with a lot of branching,
Yeah.
that might get awkward. But most scientific workloads should be pretty straightforward.
Does it support double precision?
What? Oh, double precision? Yeah. We use the TF.Flit64 variable type. I don't know a lot about the requirements for distributed. My guess is that you probably want to kind of end, but I don't know for sure. You can also you can redesign your setup to depend to different degrees on having a fast network. I don't actually know.
So you go afterwards to the. I've never gone. My wife is waiting some. Went back. It's the problem. My wife is actually watching online. She has a meeting from 5 to 6 in.
Not necessarily in the input space, but you can design your model in a way that you have a sparse matrix or a situation that could be represented using a sparse matrix. Like for example, you could have hidden units that are connected to only a subset of other hidden units, and that would be a sparse weight matrix. If you wanted to try to do something like get a speed up from only activating certain units, then you could use a sparse matrix to represent the activations. So far, no one has really been able to get a speed up from doing that.
So with speech, do you typically sparse?
I think for speech, you would usually have a dense matrix, unless maybe you were representing the output as a one hot embedding vector of a sparse vector at the edge.
I want to wait till 6:30.
Yeah. Should we test them right?
Yeah.
So that we have the 8 years.
We were thinking instead of like maybe saving conversations, and I work on that one.
Okay.
Oh yeah, oh yeah, I can definitely hear you. Much better. All right. Quality is never that great on the live stream, but nothing we can do about it. Cool. Awesome. How was life?
Good.
Busy?
Busy as usual, but good.
Cool shirt. Okay, I think everything is working. So guys, before we start, I don't know if some of you have seen, so we are getting the space back so we can continue coming here. We'll take a 2 Mondays break, so no meetup next Monday and the Monday after, and then we'll restart again with a part 3. So maybe it'll give some people time to catch up. I've been getting a lot of comments that people are like, I'm behind, I started late, and I can never like catch up. So maybe it'll give people some time to do just that. Cool. Let's see. I think we are right on the money and can start whenever.
All right. Good evening, everybody. Thank you for coming. Tonight we're covering Chapter 12, Applications. This chapter is one of the hardest chapters to do with the textbook. Everything is changing so fast in the world of deep learning applications right now. If you can believe it, at the time we started writing this book, LSTMs weren't popular yet. There wasn't any major work on reinforcement learning yet, not with deep learning anyway. And look where we are today. So because the world of applications is such a moving target, we try to give you enough of the basics where you can understand what some of the major issues are in each application area. You can speak the language of that field well enough to read about it and understand what's going on. And we even give you some of the ideas of how it is that deep learning helps a particular application area more than other kinds of machine learning may have in the past. What we're not giving you here is a complete description of the latest thing that you can do with deep learning in this application area. That's just not feasible with a book that we have to print on a dead tree after a year of editing and proofreading and all of that. So in this case, more than probably any other chapter in the book, you need to keep in mind that after you've gotten your introduction to the area here, you should go out and read papers in the application area of your choice. Whatever application area you want to work on has definitely changed a lot since this chapter was written, and you should go catch up from those latest conference papers and press releases. So the first topic that we'll cover is large-scale deep learning. Large-scale deep learning underlies basically all of the applications that we have today. Even if you eventually want to use a relatively small deep learning model when you deploy and run on mobile or run on an embedded device, usually there's some kind of large deep learning model in the meantime. You might train a very large model and then use a model compression technique like distillation to shrink it. If you look back at this figure from chapter 1, we can see how the size of models has really changed over time, starting from the 1950s and going up to about 2015 when I made this plot. Essentially, the size of the model, measured in terms of the number of neurons,
has grown exponentially. I've plotted it here on a logarithmic scale, and we can see that there's a line that we've fit to the model that approximately explains the way that the model sizes have changed over time. I think over the last few years that's actually plateaued a little bit. We got to the point where the models were big enough and we didn't make as much of an effort to push the model size. On the other hand, as of 2015, we're actually a little bit above the exponential curve. So we're probably just evening out and catching back up to the curve. Most of the strategies that you engage in when you implement a model to use for a really serious application are all different ways of scaling up to this kind of size, the size that it takes to really process one of these models. In this chapter, we don't really emphasize the collection of the training data, but that's an important prerequisite for any of these large models. If you want to express a more complicated function, you need to make a larger model, but you also need more data to fit it. So for any of these applications, we assume you've built a data set that's large enough to train the model that we'll describe how to build. There are a few different ways that you can implement a fast model. If you're working exclusively on CPU, there are a lot of different things that you can do to accelerate the speed of your code. We relied on these until relatively recently, and now essentially all deep learning workflow has moved to GPUs. On CPU, you can do things like look at the family of CPU that you're using and determine whether fixed point or floating point operations are faster, or sometimes you can do both floating point and fixed point at the same time in different pieces of the CPU. And you can move more of your arithmetic code into the appropriate kinds of operations. But this changes a lot depending on which CPU family you're using, so it's not like one of them is just faster than the other across the board. It's also very important to write cache-friendly code. A lot of people who come to me with ideas for how to accelerate deep learning models will often have complicated ideas about computing only some subset of the features and using lots of if statements in the code to activate or deactivate different parts of the network. Those ideas make sense, but you need to keep in mind that they often cause cache misses. And the cost of a cache miss is so much greater than the cost of an individual arithmetic operation that it makes it really difficult, even on CPU, to do some of these more complicated algorithmic ideas. That's part of why a lot of the ideas that we described for how to scale up your deep learning implementation seem so simple and straightforward and have so few moving parts. A lot of the moving parts just kill the cache performance. Since about 2008 or so, we've been moving more and more onto GPU, especially in the last few years. GPUs were originally designed for graphics workflow. That's the G in the GPU. For computer graphics, we essentially do two different things. We take the 3D coordinates describing the vertices of a model, and we transform them into 2D coordinates that have the appropriate perspective transformations applied. We also take the description of textures to be applied to these 3D triangles when we render the triangle in 2 dimensions. At every different point on the surface of the triangle, we figure out which pixel from the texture should be drawn at that location, and we adjust the lighting and a few other calculations. Both of these processes have one thing in common, which is that they process very many different individual items, lots of different vertices, lots of different pixels, and they do relatively simple standardized computations on each of them. We're doing a perspective transform of many vertices at once. We're doing interpolation of coordinates into many different textures at once. That means that if we can express deep learning workflows in that kind of framework, then the same hardware will benefit deep learning. Fortunately, deep learning turns out to map into this kind of hardware very, very naturally. All of our deep learning models have several different hidden units within each layer, and each hidden unit is defined by basically the same kind of operation as each of the neighboring units. So ever since GPUs have given us the flexibility of programming to be able to specify operations other than graphics on them, we've been able to run deep learning models on them. There are some considerations when you write code for GPU. One thing is that there is actually no cache on most of the GPUs, or at least for the kinds of operations you want to perform or the kind of memory you want to use, there may not be a cache. That changes a lot of the intuition for how to write code relative to what you may be used to on CPU. In particular, on CPU, you often spend a lot of your time making sure that you never recompute anything. On GPU, it's often much easier to recompute something than to fetch it from memory, because the cost of accessing memory without a cache is relatively high. It's also very important to synchronize many of the different threads within a group called a warp on a GPU. A warp is essentially a small group of threads that each need to be doing the same kind of operation at the same time. So if you have an if statement where you execute one kind of code depending on one value going into the if statement, and you execute another batch of code given another value of the condition going into the if statement, the warp will actually need to run that if statement twice. And it will just deactivate the threads for each side of the condition that isn't meant to be updated. So if you want to design code that runs really well on GPU, you need to design it in a way that you very rarely put the warps out of sync. Otherwise, you'll spend a lot of time rerunning all of the warps. If you look at the latest version of the programming guide for each of the latest generations of hardware, you'll see a lot of different criteria like this. And the good news is a lot of this is very complicated, but you don't need to do very much of it yourself anymore. But when I first started working on deep learning, my friends and I built our own machine and got one of the very first CUDA cards and started doing our own CUDA kernels from scratch. And we'd spend a lot of our time adjusting the CUDA code based specifically on the architecture we were working with. Now you can rely on libraries like cuDNN and even on frameworks like TensorFlow that wrap cuDNN. So you mostly just need to think about which operations you're going to run and where you're going to place them. You work at a much higher level of abstraction, but it's still useful to understand the underlying computational model so that when you're thinking about the performance on GPU, you understand that the reason you might want to schedule different operations depends a lot on things like memory-to-memory bandwidth and so on, rather than cache friendliness. To make a model really, really big, and also to make it train fast, you're definitely going to want to use a distributed implementation. So there's a lot of different ways that you can distribute your job. One is you can actually distribute it within a single machine across multiple GPUs. If you're building a multi-GPU machine yourself, you want to make sure that you get a good motherboard where you can actually have really fast communication between all of the different GPUs in the main memory of your computer. And you can expect to spend quite a lot of money on the motherboard itself, as well as the components that do the actual computing. You can also distribute your job across multiple machines if you have lots of machines networked together in a reasonably efficient way. There's two different ways of dividing up your workload across either multiple GPUs or across multiple machines. One of them is called model parallelism, which is where you run different pieces of the model on different devices. So you might have the first 10 layers of your network on one GPU, and then the next 10 layers of your network on another GPU. And every example that you run through the network will actually run on both of these GPUs. The other kind of parallelism that you can use is data parallelism. This means that you actually run different examples on different devices. We usually refer to this as training several different replicas of the same model at the same time. So you might define a network that takes an input example and a training step that proposes an update to the parameters. And then you can have a parameter server that keeps track of a canonical version of the parameters that many different workers update. Each worker will grab a different batch of training data, compute the gradient on the parameters for that batch of training data, and then send the gradient to the parameter server for an update. These different jobs will also read from the parameter server to update the latest version of their parameters. Distributed implementations of gradient descent are still an ongoing research area, and there's always new updates for them coming out all the time. The early work that really got this working well in practice came from the Google Brain team. More recently, we've seen a paper from Facebook about training ImageNet very, very quickly by using giant batch sizes and lots of machines. So it's a really hot area. It's not one that I personally follow myself a lot, just because it's not the area where I do my research, and I won't be able to tell you quite as much detail about it as I've been able to for some of the other chapters. But it's definitely a place where there's a lot of exciting papers coming out fast and furious lately. After you've trained all of these really big models, you'll often want to go and put them on a phone or on an embedded device. And you may not be able to use a lot of power. You may not have an ALU that can do very many operations per second. And there could be a lot of other constraints on exactly what you need to do. You might think that this means we should just train a really small model from the start in order to have a really small model that we want to put on your phone. It turns out that often doesn't work very well. For some reason, it's harder to train a small model And in particular, they often seem to have higher test error than if you just train a really big model from the start. One particularly useful kind of big model is an ensemble model, where you just train a very large collection of independent medium-sized models. And you can also really increase the size of the model if you use dropout at training time. So this very big model defines a function mapping from inputs to outputs, and it has a relatively low amount of overfitting. So it understands a lot of things besides just the association of each training set input to a particular output value. You can pull more information out of this model either by loading new points that didn't occur in the training set and seeing what output it assigns to them, so you can effectively get a larger training set. Or you can look at the probabilities it assigns to the classes other than the correct class. This general strategy of using a very large model to define a training set with extra information for a smaller model is called model compression. And the specific version of it where you use the probabilities of the classes other than the correct output class to learn more about the model is called distillation. The interesting thing about distillation is that you can actually train the smaller model to recognize classes that it's never seen before. If you train it on MNIST with images of, for example, 3s, and it sees that some of these 3s have somewhat high probability of the 8 class, but very small probability of the 2 class. It can learn that 3s look a little bit like 8s. They both have the hook shape on the right side. And then when you see a new 8, the model can infer that this isn't a 3, but we know that there's this 8 class out there that looks a little bit like 3s, and it can guess the new input you've shown it is actually an 8. Overall, training these small models to mimic the large ones gives you really good accuracy at test time, while still giving you the low resource use that you want when you deploy. Another way that we can reduce the size of networks at test time is to use dynamic structure, also called conditional computation. Some of these methods work really well and have been in practice since even before deep learning was popular. Some of these are still more research areas and can only really be done by an expert practitioner. So one very trusty, tried and true method of dynamic structure is what's called a cascade. If you had a point-and-shoot digital camera back before mobile phones were popular, you've probably seen a camera that you hold up like this and look at a little LCD screen on the back, and it might highlight different people's faces. The way that it was highlighting those faces was using an algorithm called the Viola-Jones face detector. And that was able to run on these relatively old digital cameras by using a cascade. The idea of the cascade is that you have several models in a row that each work as detectors, and each of them solves a relatively simple task. But when you put all of them together, they're able to perform a relatively complicated task. Specifically, if at the end of the day you want to detect whether some object like a face is present, you can start out with a cascade that has relatively low precision, but relatively high recall. So the first model of the cascade that you'll run will say, I think there's probably nothing here for most inputs, and then you just stop at that point. As long as this has high recall, meaning that it rarely misses a face that's there, you can get away with just stopping at that point. It's okay if this model doesn't have very high precision. It's okay if most of the time it says, maybe there's a face here, let's keep going, that you look at what it saw and 9 times out of 10 it's like a door with 2 doorknobs and a handle that looks a little bit like a face but isn't really one. You can go ahead and catch those mistakes in the later steps of the cascade. As you move to different models in the cascade, each one becomes a little bit more selective and starts to prioritize precision over recall. So by the end of the cascade, if the model says, I think there's something here, it really has to be right. And at that point, it doesn't have as much pressure to recognize all the different kinds of faces that can be out there because the earlier stages of the cascade have filtered out a lot of the weird stuff, and you're left with mostly just things that are faces. You don't need to learn about all the unusual ways that doors can look like faces because they've been gradually filtered out. So every step of the cascade gets to be relatively smaller because the problem is either easy because early in the cascade it's okay if you don't have the right final answer, and late in the cascade the problem is easy because the earlier members of the cascade have simplified it for you. The cascade is very simple to implement, and it's probably in almost every application of computer vision that I can think of. even if you don't think of yourself as using a cascade, there was probably some model that was used in the pre-processing of the data that you think of as being the entire problem that you're working on. For example, when I worked on address number transcription for Street View, I just got images of addresses and I had to transcribe them into text. But there was another model that came before that was cropping the image to look just at the address. You can think of that as being a kind of cascade. Cascades are very straightforward and have worked really well in a lot of applications. There are other kinds of dynamic structure that are a lot harder. In particular, there's the hard mixture of experts. A mixture of experts is a model where there are many different sub-models that each specialize in different things. Like if you're going to translate a sentence from French to English, you might have one expert that specializes in adjectives, and another expert that specializes in articles like or the. I don't know exactly what kind of experts you might have. And the idea of a hard mixture of experts is that for every example or maybe every word that you process, you actually make a decision about which expert you're going to consult for that translation, which model, sub-model you're going to run. And you commit to that decision. That's why it's called hard. It's not a soft mixture of experts where all of the different experts vote, because then you'd have to actually spend computation for every expert in the mixture. Instead, you pick an expert and you go with that expert's prediction. For this, you have a secondary network that's often called a gating network or a routing network. The gating network decides which expert to activate or which expert to connect to which other expert. You can actually take information from an expert and send it to another one, just like packets in a network. Recently, there was a paper from Google Brain about outrageously large networks for a translation that was based on this idea of a routing network that activates different networks and sends information from one to another. It's still an area that's very much in the domain of research and not necessarily the thing that you encounter every day when building a real system. It takes a lot of expertise to make it work well. But in their paper, it worked very, very well. Not only did it result in them being able to train a model with billions of parameters, when the previous baseline had millions, but they were actually able to train this very large model much, much faster than they were able to train the previous models. The reason they were able to train it faster is that every training update involves only a very small subset of the parameters. So even though there's a lot of parameters being stored, very few of them are accessed for each example you process, and very few of them are updated for every training example that you encounter. Another very important area for improving deep learning in general is making specialized hardware implementations, usually based on application-specific integrated circuits, or ASICs. Generally, the way that these are able to get a speed up is by trading off speed for precision. A lot of the time, we don't necessarily care about being able to run 64-bit numbers and get exactly the correct result. We want to get roughly the right ballpark for each of the arithmetic operations that we do. For deep learning, that's okay, and in fact, a lot of the time errors are actually noise regularization. Even when we use exact computation, we do things like add noise to the input as a dataset augmentation strategy, or we add noise to the hidden layers, especially multiplicative noise like dropout. Both of those just regularize the model. So if your hardware is going to do something like that intrinsically, it's okay. It just reduces your test error. And if you get a speed up by doing it, so much the better. At Google, we have the Tensor Processing Unit, which either is available or will be available through Google Cloud soon. And there are a lot of other areas where different companies and organizations are building their own specialized hardware to accelerate deep learning workflows. One of the main application areas that we actually bring all of these giant models to bear on is computer vision. I won't have a lot about computer vision in this chapter because modern computer vision is basically synonymous with convolutional networks, and we already have a whole other chapter on convolutional networks. One thing that we didn't really comment on in the convolutional networks chapter is that we sometimes have specialized pre-processing for different kinds of computer vision models. Since about 2013, pre-processing hasn't really been all that popular. But prior to 2013, it was used quite a lot. So it's useful to be aware that these different pre-processing techniques exist and understand what those papers are talking about if you're reading them for context. The main kind of preprocessing that we still actually use a lot is dataset augmentation. And so dataset augmentation is, as we described in Chapter 7, just any technique for making your training set bigger by doing lots of different transformations to it. It's important that each of these transformations preserves the class of the input. But basically, you can take one image like this moth on the left side of the slide, and you can turn it into very many different training examples just by transforming it several different ways. Computer vision is especially nice because it's really easy to define transformations that don't change the class of the object that you're interested in. All kinds of geometric and color transformations are fair game. One of the main exceptions is if you're doing something like optical character recognition, you maybe want to leave out some of the transformations like horizontal flipping or vertical flipping, because you can turn a 6 into a 9 or a B into a D, and so on. Other than that, quite a lot of different transformations are fair game and will reduce your test error quite a lot. For speech recognition and speech synthesis, the main thing to know really is just that until a few years ago, we had graphical models that were designed very specifically for processing sequences, like hidden Markov models, Gaussian mixture models to serve as the observation model of the hidden Markov model. And in the last few years, we've gotten rid of all of these explicit probabilistic models and replaced them with just recurrent nets. Usually that's an LSTM. Sometimes that's one of the other LSTM-like models, such as a gated recurrent unit. We've also seen that this works really well for speech synthesis. In particular, the WaveNet model from DeepMind last year is really good at speech synthesis. That's basically just a recurrent network that generates speech samples one time step at a time. One of the other interesting ideas in WaveNet is that the signal is discretized into several different categories of values. So the softmax unit is actually outputting a distribution over many different discrete values of the amplitude or the frequency. I forget exactly how it works at each time step, but that removed a lot of the previous pipeline where people spent a lot of time designing specific probability distributions over the real numbers. They just turned it into discrete values and learned categories of them. That was kind of interesting because it works even though the model doesn't actually know anything about how category 1 is very similar to category 2, but very different from category 10. There's nothing actually encoding the order of the categories in the softmax distribution. And just by training on a lot of data, the model learns to create probability distributions that vary smoothly as you go from one bucket to the next bucket in that histogram. For natural language processing, we usually have sequences of discrete tokens. We either have sequences of individual characters or sequences of words. Another one that's a little bit less intuitive is sequences of bytes. There's actually quite a lot of successful work on doing things like representing Unicode characters as just strings of bytes. And essentially all of natural language processing with deep learning today is using recurrent nets to model probability distributions over sequences of these discrete tokens. We've seen things like translation systems, both at Google and at Facebook, moving from previous phrase-based technologies to using large neural networks trained on multiple GPUs in order to represent these probability distributions. This is one case where it's particularly useful to understand what came before, to get a little bit of an intuition for what it was that deep learning added. One of the main models that we used before was called an n-gram model. And n-gram is just a sequence of n words. Usually we use a value like 3 for n. So we look at how often little sequences of 3 words appeared in the training set. You can compute the probability of each of these 3-word sentences, or 3-word phrases, just by gathering counts of how often those words occurred in the training set, and comparing to how many 3-word sequences were present in the training set. If you want to compute something like the probability of the sentence, "the dog ran away," you'd begin with dividing this up into several different trigrams for "the dog ran," "dog ran away," and then you have the dog ran context for the last word. There are a lot of different ways that this can fail. One is that if there are very rare words or very rare combinations of words, you might be looking for the probability of the third word and find that you've never seen the word that appears in a particular test sentence after the preceding two words before. One way that you can deal with that is called smoothing, where you just add imaginary counts to all possible sequences of 3 words. So you just start off pretending that you've seen every possible word alpha times, and you can set alpha to an appropriate value, and that just spreads the probability mass around. There's another thing called backoff, where if you fail to find the 2 words preceding the word that you want to look up, then you can't use your trigram model and assign a probability of 0. So you can fall back to a bigram model. Maybe you can find the 1 word preceding the current word and look up the probability in a bigram model. And if that fails, you can back off further to a unigram model, where you just use the probability of this individual word that you're looking at occurring. You can also group words into different categories. So you can see how these different strategies for smoothing out the trigrams are a little bit clumsy. That just grouping words into categories might lose some nuance. There might be a lot of different words that are very near to synonyms to each other, but some of them have different connotations than others. So we'd like to have some way to capture this idea that words are very similar in many respects, but then different in a few respects. That's what neural networks do. When we have words represented with one hot bag of word vectors, then any 2 words that are different from each other are equally distant in that vector space. If you have the word dog and the word cat, maybe one of them will be word 596, one of them will be word 912, and each of them will have the corresponding bit in this huge vector of mostly zeros and a single 1 active. And they won't have any of those 2 bits in common. So if you look at their distance from each other, they're Hamming distance 2, or Euclidean distance square root 2 from each other. Any 2 words that are not identical to each other are going to be exactly the same distance from each other. And it means that when we compare a dog and a cat, that's just as dissimilar as if we compare dog and dictionary. There won't really be anything to say that these 2 words have in common that they're animals, that they have fur, that they have 4 legs, and so on. Neural networks take this word representation with a 1 hot vector, and they convert it into a vector of real numbers that gives us a set of coordinates in space. If we take these coordinates in space and zoom in and convert them to 2 dimensions, we can actually plot them in a map and see that this map arranges words similarly to each other based on their meaning. So here I've zoomed into different areas on a map of different words. We see on the right that there's one area around the coordinates 36 and 19, where we have a bunch of words for years. Like 1995, 2002, 2007. These are just numbers that are presented as unique tokens to the model. It's not told specifically that they're words, but it's figured out that these particular numbers, when you see them in the kinds of text that we use in modern speech, we tend to use these numbers to represent words, and we automatically associate them with different ideas. On the left, if we zoom into an area near -30, we find that there are several different words living in this area where their vectors have all ended up close to each other, representing different countries. And to some extent, you can even find sometimes that similar countries are near each other, and dissimilar countries are farther from each other. In this particular model, I don't see that phenomenon happening quite as much. Like we have France and China right next to each other. But in some other models, you do sometimes see that countries that are culturally similar or have been associated with similar conflicts are near each other. One of the other challenges that comes up a lot for natural language processing is that if we choose to represent our model as a sequence of words, then there's a very large number of words. So our 1 hot word vector telling us which word is present at each position might be extremely high dimensional. We might have a vocabulary of 1 million different words if we want to include all the kind of slang and misspellings that often come up in natural text on the internet. So there are a lot of different strategies for how we can deal with such a large output vector. One is we can have a short list of words that are used more common than others and try to rely on producing just the probabilities for that short list most of the time. Another thing we can do is we can have a hierarchical softmax, where we assign probabilities to different categories of words and then expand just the more likely categories and assign more fine-grained probabilities within that category. We can also use importance sampling, where we compute only some of the more likely words and pay attention to those. Or we can use a technique called noise contrastive estimation, where we train the model by looking at the probability of a noise value that we sampled and looking at the real value that we want to predict and using the ratio between those to update the model. That way we avoid actually looking at the entire probability vector over all the million possible next words that come up. To give you an idea of how the hierarchical softmax works, we start out at the root of this tree of categories, and first we decide if we're going to go left or right in the tree. And then let's suppose that we go left, we end up at the node labeled 0. And then we choose another set of probabilities to decide whether we're going to go left or right, and we could possibly go to the right and end up at the node labeled 0, 1. And then finally we choose one more set of probabilities to decide whether we go left or right, and we end up, let's say we go left, we could end up at word 2, 0, 1, 0. To compute the probability of word 2 in this model, we multiply together the values at each path that we took. So we have one probability here, moving this way, as I'm indicating with the cursor on the screen. So we have one probability here, another probability here, and another probability here. Multiplying those together gives us the overall probability of ending up at word 2 from whatever our previous state in the sequence was. And because we only need to use those probabilities, we don't actually need to define probabilities for all these other leaves when we're evaluating the probability of word 2. And it can reduce the total amount of computation quite a lot. One of the main NLP tasks is neural machine translation. This looks very, very simple in terms of mapping from an input space to a hidden space, and then mapping from that hidden space to another visible space in a different language. So we might start with a French sentence and run the encoder, and then we get a hidden layer representation of the meaning of the French sentence, and then we can run the decoder and get some output in, for example, English. You can use the same kind of encoder and decoder architecture for other domains besides just one natural language and another natural language. One particularly interesting application is to start with an image and produce a caption for that image. So you actually just have images going in and descriptions of images coming out the other end. You can also do sentences at the input and descriptions of parse trees at the output. There's a paper called Grammar as a Foreign Language that describes how to do that. And the different sequence-to-sequence architectures that you can use for the encoder and decoder give you really a lot of flexibility in the kinds of translation that you can do. Recently, we saw with the new Google Neural Machine Translation System that the idea of this intermediate semantic representation in the middle can be very powerful. The authors of that paper found that they could train, for example, an encoder and decoder to translate from English to French, and they could train an encoder and decoder to translate from English to Chinese, and they could train an encoder and decoder to translate from, for example, Japanese to French. So now we have a few different encoders and a few different decoders that all use the same hidden representation. And so you can start to mix and match languages. Like you may have never trained French to Chinese, but you have an encoder for French and a decoder for Chinese, and they use the same shared hidden representation. You can now translate that pair of languages despite never having seen a pair of training sentences for those particular languages. A lot of these sequence-to-sequence models rely really heavily on what's called an attention mechanism. This is described to some extent in the Recurrent Network chapter. The basic idea is that when you're doing something like translation, you often encounter words that you've never really seen before. That you might be reading a piece of text about how Jeff Dean recently wrote a paper about very large translation models, and maybe Jeff Dean has never appeared in the training set. But you would like the model to successfully talk about him in the output sentence when it produces the French translation. An attention mechanism allows the network to understand what position in the sentence it's looking at each position. For a lot of the positions, it might just translate based on the knowledge that's stored in its weights of how the English and French languages work. And then when it comes to the point where it's writing about a specific person's name, it could actually more or less just copy that name from the input to the output, because it's learned that that's how it ought to handle proper nouns. Attention also helps with things like changing the order of different words. Like in English, we tend to have adjective and then noun. We say, red apple. But in Spanish, we have like manzana roja, and the attention allows it to understand that we're going to process these different words in different sequences, but it understands when you're looking at translating the word that's going to be manzana, you look at apple. And that is able to solve the what they call the alignment problem of which word in the input sequence maps to which word in the output sequence. That used to be managed with a lot of hand-designed rules and guided search over different possible alignments explicitly in some of the older translation systems. So that's actually the end of the content on natural language processing applications. I think a lot of tonight will actually just be the Q&A, but you can ask me about the applications you're interested in, and if I know a lot about them, I'll be able to tell you. If I don't know, I'll maybe be able to give you hints for what to read next. So who has a burning question about applications? Yeah.
Last year there was lots of discussion about chatbots, and in the startup world, do you have any idea about the state of the technology on that side of the world, and if it's feasible, if it's useful to invest in it, time and resources?
Well, I won't be giving you investment advice, but I haven't seen a chatbot application that I've been really impressed with so far. And I think from a scientific point of view, one thing that makes chatbots really hard is that it's difficult to evaluate how well you're doing. And that means it's also difficult to do something like get a reward for reinforcement learning. So for example, if you have a chatbot that's meant to do a transaction, like it's meant to help you solve a support issue, you can give it a reward like, if the person gives up and quits talking to the bot, then the bot isn't working very well. So you might give it a reward of user engagement, but then it has an incentive to not solve your problem too quickly. If you get a reward of solve the problem really fast, then you get a bot that's kind of rude and is just like, turn it off and on again, bye. And neither of those is quite what you want. I don't work in that area enough to get really into a lot of finesse on why it's hard to evaluate them, but my understanding is that basically a lot of other tasks like object recognition, you just measure error rate on ImageNet and it's easy to tell if we're making progress or not. And then chatbots, it's really, really hard to tell how well you're doing. So a lot of the development just kind of goes into a random walk. I think in China, there are chatbots that are much more successful than in the English-speaking world. My impression is that a lot of them are more conversational than goal-oriented, that you talk to them about your feelings and they empathize with you. They don't necessarily advise you on like how to get your laptop screen to quit turning blue, but they're interesting for users to interact with. Yeah.
So I have actually two questions. Like you were talking about the language-to-language translation and about like English to French and then Chinese to English. And then, as I understand, this is a training that is within one neural net, right? So you're not combining two neural nets that are trained on a different set of the platforms, right? You're training within the one.
So for things like the Google Neural Machine Translation System, I tend to think of that one as more like several neural nets that have been trained in a way that causes them to have more or less the same hidden vector. There's one encoder network for each language. There's one decoder net for each language. I guess you can think of the union of all these encoders and decoders as being one big system. But usually when you train them, you only really need to be running one at a time. I think. I haven't actually worked on that project, so I might be wrong.
Another question I had, like, which neural nets are faster on GPUs? Like, I would assume that LSTM is a little slower because you have a lot of decisions, and like CNN is a little faster. But could you like give some kind of practical advice on how to?
Yeah, as a general rule of thumb, more layers will be slower.
People online are asking if you could repeat the questions.
Oh, okay, yeah. So the question is, which kinds of neural nets are faster on GPU? And part of the question was an example of how maybe an LSTM is slow because it has to go through several time steps. And yeah, that's exactly right. As a general rule of thumb, more layers, more runtime. And it's just because each of those layers corresponds to more kernels that you have to schedule on the GPU. To some extent, if you have a very wide layer and you eventually saturate what the GPU is able to do at once, then the width of that layer will start to affect your runtime too. So a lot of convolutional nets are big enough that the width of the layer is actually affecting your runtime. A lot of smaller models where each layer is not all that big, like a recurrent net, they're more driven by latency than that you have to schedule time step t+1 after time step t than they are limited by bandwidth. A lot of engineering problems come down to trying to maximize the bandwidth and hide the latency by, for example, increasing your batch size and coalescing lots of different examples together so that you can make full use of all the ALUs in your hardware. But it's often pretty difficult to get up to full utilization.
So I have a question also on the encoder-decoder network, and I'm wondering, at what point do you call something an encoder and decoder network? And I asked this question because I sort of came across the concept from reading about autoencoders, but then when you read something like the One Model to Rule Them All paper that came out from Google, where you had like different modalities and you have encoders for different modalities. And when you're reading like sequence to sequence, it just looks like an LSTM running into another LSTM. So my question is like, when do you call something an encoder-decoder network? Must there be like some sort of compressed representation in the middle that expands outwards?
Yeah, so the question is, when do you call something an encoder-decoder network versus something else? And I mean, it's really cultural. It's not really like there's a mathematical rule. You could say that a convolutional net encodes on layer 1 and then decodes the class at the last layer. So I guess I'm giving you more of an answer where I describe the way that other people talk about things more than I'm giving you a technical answer. I'd say basically, if the model produces a code that you would actually look at in the course of using the model, and you might like send that code to another machine, or you might store that code and look it up later, or you might visualize the distribution of that code, then people tend to call it an encoder-decoder model. If the machine produces a lot of intermediate computations that you mostly just throw away and don't ever look at them unless you're debugging or something like that, then you tend not to think of that as encoding and decoding at every step. But really, it's the same thing happening in terms of the map at every step. You're just transforming from one representation to another. You could call almost everything we do an encoder or a decoder, or some layers you could even view as encoding one thing while they're simultaneously decoding into another language.
Cool. Yeah. There's 3 questions from this live stream. The first one, are neural networks good for dynamic systems like stock value forecasting? That's from Vikas.
What's stock value forecasting?
I guess they want to play the stock market.
Oh, stock value forecasting. Sorry, I misheard as stock value forecasting. Okay, so the question is, are neural nets good for time series prediction like stock value forecasting? The thing with stock value forecasting that's difficult is 2 different things, really. One is that there's a lot more noise in that system than there is with a lot of the things that we usually do. in artificial intelligence. If you look at an image and you want to know whether it's a cat or a dog, all of the information you need to know to make your decision for sure is there. With stocks, you often don't actually have enough signal to know for sure whether the price is going to go up or down. And if there is an algorithm that can tell from the information that we usually have available, no one knows. And there's a lot of reason to believe that you wouldn't actually be able to know from the signals that we're able to observe, since so much of it is confidential and so on. So the noise is one thing that makes it a lot more of a challenge. Another thing that makes it a challenge is that the stock market has non-stationary dynamics. So if you find a really great algorithm for predicting how stock prices are going to change this year, then next year that algorithm may not work anymore. Like Planet Money podcast has the BOTUS bot that buys and sells stocks based on whether Donald Trump criticizes or praises them. And that's clearly something that's very specific to 2017 and the fact that we have a president who does that right now. And after his term ends, that won't really be applicable anymore. But there is definitely a lot of use of deep learning in finance. I'm not sure how much of it is predicting stock prices specifically. I know that there's been a lot of work on using RNNs to predict currency prices for currency exchange. If you can predict ahead of time that you'll want a lot of some currency, that you can buy that up at low prices before your customers want it, and you profit the difference. I also know that there's a lot of things like using deep learning to understand the sentiment of different articles, and then use that understanding of the sentiment to inform other algorithms that make stock price predictions. But I'm not sure that the whole thing is end-to-end deep learning. One other thing that's worth mentioning is that a lot of trading algorithms run at extremely high frequency, where you have different firms competing to set up faster hard lines to the exchange in order to trade milliseconds faster, and that actually makes a difference in the profitability of their algorithm. If you're in that kind of regime where you want to trade really, really fast like that, then a deep learning algorithm is probably going to struggle to add more accuracy than it subtracts speed, and that will limit the applicability of deep learning to more of like medium or low frequency trading. What about the weather? I don't actually know a lot about weather forecasting. It pops into my mind there was a NIPS paper last year, maybe 2 years ago, about using convolutional LSTMs for precipitation nowcasting. That's different from forecasting. I think nowcasting is like, based on the information you've got about the world right now, can you predict exactly how much rain is falling in different areas that you can't measure directly? Forecasting, I don't know as much. One thing that's really weird about weather forecasting, and here I'm just relying on having read Nate Silver's book and not relying on anything I know as having been a scientist in the wild, is that the equations that can be used to predict the weather are reasonably well understood, but measuring the state of the world and getting all the variables that affect the weather prediction is really hard. We don't have little drones flying in every 10 cubic meters of atmosphere, getting information about the temperature and humidity everywhere. And if you run the equations with slightly different initial conditions, you can get totally different output values. So if my understanding of the difficulty from that book is correct, it seems to me like something that machine learning wouldn't be able to handle all that well. If uncertainty about the input causes huge changes in the output, then you can have a perfect machine learning model, and if you just give it slightly wrong inputs, it'll give you a wrong forecast.
I had a question earlier about the NLP part when you mentioned that the Euclidean distance between the cat and the dog would be root 2. And you also said the Hamming distance would be 2. But isn't the Hamming distance the number of switches you need to do to have the characters learn? So it would be 3?
So if you switch the dog bit off and switch the cat bit on, then you've done 2 switches to go from dog to cat.
That was character by character.
Oh, I see. So I'm thinking of a vector representing the idea of the word dog. So dog might be word 1 in the vocabulary. So we have a vector with all zeros, and then bit 1 is active, it's set to 1. And then cat might be word 2 in the vocabulary. So it's a vector with all zeros, and then in position 2, the bit is active.
Like a one-hot encoding code.
Exactly, yeah.
Do you have any advice when you might want to search serve something with on machines that have lower precision, that you, for training, you might have something that could offer higher precision?
Yeah, so the question is, what if you can train with higher precision and then serve with lower precision? Sometimes just the naive process of training and then serving will work fine. It's definitely useful to have higher precision at training time because you want to be able to, at every step you have parameters, you want to add a gradient to them, and you want to add a little tiny value to the parameter and make a slight update. If you have really low precision of the parameters, then those slight updates will get rounded away to nothing. And so a lot of the time this is just what we do by default. If you find that at deployment time you're getting trouble from the parameters being quantized or from the activations being quantized, then you can simulate that a little bit at training time by adding noise to the parameters and adding noise to the hidden activations. That will give the model the benefit that it has to learn parameters that work, even if some of the parameter values or some of the hidden unit values change. But you still get to take advantage of the higher precision of the weights so that you can make little tiny changes to them at each training step without actually having the little tiny change get rounded away to nothing. Does that make sense? Yeah. With the Hackapalooza shirt, yeah.
Yeah, okay. GANs have sort of taken the deep learning world by storm, and I remember like reading your NIPS tutorial and being like really excited by all the math that you were talking about, how they work, and they've been applied to other things like reinforcement learning really well. I primarily work with audio, and there's some projects that are out there that try to apply it to audio, but haven't really been successful yet. A lot of the success, obviously, as you know, has come from images. Off the top of your head, what are kind of like your intuitions or off the bat kind of thoughts of how we can apply GANs to do the impressive things that WaveNet, for example, is doing with audio? Maybe like given a corpus of speech or utterances, produce another utterance, or given a corpus of maybe particular instrument sounds, maybe like percussion sounds, generate another percussion sound or something like that.
Yeah, definitely. So for the live stream audience, the question is how can you get GANs to model audio well, like WaveNet does? So I guess I have a few basic thoughts about that. I haven't worked on it myself very much. One is I definitely recommend working with continuous values rather than with discrete values. For example, some people have tried to use a vocoder for the speech synthesis, and some of the vocoder instructions are discrete variables, and that just makes it a lot harder to train the GAN. GANs work best when the output is differentiable with respect to the parameters. If you've got a discrete output value, then that's a non-differentiable operation where you convert to a discrete output there. Another thing is one of the advantages of GANs that they might have relative to WaveNet is that they can. I might just cut out.
Yeah.
Maybe the battery died. I've tried turning it off and on again. The chatbot would give up on me at this point. I'll just talk louder for now. So one of the advantages that GANs might have over recurrent models like WaveNet is that they don't have to be recurrent. WaveNet and other autoregressive networks have to produce everything one value at a time, and that can slow them down. It can increase the amount of memory that you need to backpropagate through all those layers. So it might make sense to look into using convolutional GANs to generate the sound. Depending on the application that you're working in, you may not actually need the generation process to respect the laws of causality. It might be okay if information flows backwards in time while you're producing a waveform. So then you can actually get really low latency if you just produce like 10 seconds of audio in one blast with a convolution op that produces all the different time steps in parallel to each other, rather than producing each time step and then the next time step and then the next time step and then the next time step. So both of those things I think could help quite a bit. Just in terms of which GAN techniques are working the best these days, we've seen really a lot of different papers in the last few months that all propose adding gradient penalties to the discriminator. So like how to train your dragon, improved techniques for Wasserstein GANs, Kramer GANs, the numerics of GANs. I'm probably forgetting some other ones that have gradient penalties. I haven't really sorted out for sure which GAN loss function I think is the best, and I haven't really sorted out which of the very many different gradient penalties seems the best, but the gradient penalties seem to be a good idea. And I don't really have a strong recommendation about like whether you should use the improved WGAN version where you pick a random point on a line before you apply the gradient penalty, or whether you use the improve your DRAGN one where you're closer to the output of the generator when you apply it. But those all seem to help quite a bit and probably improve the chances of succeeding with your audio model.
Thank you.
So there are like 3 more questions from online. One is if you have any opinions about CNNs versus RNNs in sequence-to-sequence encoding, like in the recent translation papers, there's been kind of 2 from Facebook with convolutions instead of 1 from Google, 1 from Facebook, and then 1 without convolutions or RNNs.
So the question is
that trend about CNNs replacing RNNs.
Yes, the question is, do I have any opinions on CNNs versus RNNs for sequence-to-sequence? Basically, I don't have a strong opinion. I don't really work in that area myself enough to be strongly opinionated. My bird's eye view is that you usually get greater speed with the CNNs because you can run all the different time steps in parallel to each other. I think you usually get better quality results with the RNNs. So I think RNNs are usually worth it if you can afford it. Or RNNs, maybe not worth it, but RNNs usually offer better quality. And then the question is, are they worth the runtime difference? And that's really going to depend on your application. I think I mentioned this when I was here last time. Last time I was here, not the last time for you guys, like two chapters ago. I mentioned that every RNN has a convolutional net hiding inside of it. You can think of an RNN as a convolutional net where you add some sideways connections. So the question isn't really like RNN versus CNN, which one is better? The question is, you've got a CNN, do you want to put some sideways connections in it? And usually like the worst that can happen from doing that is maybe you start overfitting or the computational cost goes up. If you think you're not going to overfit, then the only real question is, do you want to pay the computational cost of those extra connections?
So next question asks, if we add batch normalization to layers in the vision task, do we still need to do something like mean subtraction or contrast normalization?
Yeah, okay, the question is if you're using batch norm, you need to do pre-processing and like subtracting the mean from the image since that's already in the batch norm. But the answer is no, you don't really need to do that. And even before batch norm was popular, people had stopped doing that. I don't fully understand why it was no longer necessary to do pre-processing. Until about 2013, most of the models that we were using really relied heavily on pre-processing to get good performance. Around that year, they started to do a lot better. I think the pre-processing might have been helping small models to get good accuracy with the limited number of parameters that they had. But that's just a guess as to why it suddenly didn't matter as much to use it. Any more web questions? Yeah.
There's one more. Do you have any opinions on the Siamese networks that figure out if some piece of text has the same author?
The question is, do I have any opinions on the Siamese networks that figure out if a piece of text has the same author? I don't actually know about that work. It will probably be a nightmare for a lot of Reddit commenters who think they're anonymous. Maybe we'll find out about a lot of politicians who have been writing their little manifestos anonymously.
We have some questions over there.
We talked about data augmentation and how it almost always improves the test performance. But it comes with a cost, because the data is augmented, we have more data, and linearly, the runtime will increase linearly with the size of the data set. So can we think of a clever hack to change the architecture of the deep learning model a little bit? So when we feed like a moth picture, and the neural network will learn the moth with some noise. So the manifold it's going to learn is going to be thicker than otherwise.
So the question is, data set augmentation comes at a cost that you have more data, so the runtime increases linearly. And can we hack the model to build in some of the benefits of data set augmentation? So first off, I would actually dispute the premise that the runtime increases linearly. And the reason is,
Usually we make multiple passes over the same training set. So if you have, for example, the ImageNet data set with 1.2 million images in it, you won't make one pass over the data set and then stop. You'll have to run over it, several times, maybe like hundreds or even thousands sometimes, depending on exactly what kind of model you're training and how long it needs. With dataset augmentation, every time you make a pass over the dataset, you modify each example randomly in a different way. And so the runtime is more or less the same as if you were not doing dataset augmentation. The main difference is that it might take longer before you reach the minimum value of your test set error. It might take more passes before you converge if you're generalizing better due to these transformations. But in that case, I still think it's not really a higher computational cost. If you just stopped at the point when your test error was the same as what you got with no augmentation, I think the total runtime to get to that point would be about the same. In terms of building some of the invariances into the model, that's an excellent strategy when you're able to do it. Convolutional nets build in the translation invariance. Recurrent nets build in the invariance to different moments in time. And beyond that, we haven't really had another smash hit yet. A lot of the time you'll see papers that try to do things like build in rotation invariance in images, or papers about trying to learn different transformations to be invariant too. That's something I actually put in my thesis proposal for my PhD and never got it to work well enough to publish much of anything. So it's an area that people work on, but it's been really hard to actually get it to work for more invariances than we already have built into conv nets and recurrent nets. Does that answer your question? Yeah. Yeah. Okay. Cool.
Data augmentation is talked a lot about in images and being able to, use small data sets to do it. Are there ways to do augmentation for NLP tasks?
Yeah. So the question is, can you do dataset augmentation for NLP? And my guess is that a lot of product teams do things like add random misspellings to their training data. I don't actually know because I don't work on that. One thing I have worked on is with my intern Takeru Miyato and my colleague Andrew Dai at Google Brain, we wrote a paper about virtual adversarial training for text. The idea is you can't necessarily change the text very easily without making an edit that actually changes the meaning of the text. What you can do is you can change the embeddings of the words that you've loaded. So we actually computed adversarial examples in word embedding space and trained the model to correctly classify the adversarial examples. We found that reduced the error rate of a lot of semantic classification tasks, like reading reviews and saying if they're positive or negative. And we also analyzed the word embeddings that we learned, and we found that a lot of the embeddings make more sense. For example, before we did the augmentation, the words good and the word bad were nearest neighbors to each other because they can often appear at the same point in a sentence. You can say, like, this movie was really good or this movie was really bad. After we did the training with augmentation, it actually learned to push good and bad further apart so that they couldn't, little perturbations of those embeddings couldn't change a good review into a bad review and get assigned to the wrong label.
So can startups compete on the, considering that Google has data centers of GPUs and things like that, can startups still build state-of-the-art models, or do you think it's only big companies?
So the question is, can startups build state-of-the-art models? I guess it depends partly how well-funded they are, but also I think it is very possible to do good work individually. There's also a lot of programs where different companies, including Google, will give startups time on their different services. Like, I actually don't know about this from my Google affiliation. I know about this from friends who've done startups, so they can get free time on Google Cloud in order to develop their business. Besides that, it is possible to do pretty interesting work with even just a single GPU a lot of the time. For example, one of my favorite GAN papers, the StackGAN paper on generating images of birds from descriptions of birds in text. It has some of the highest resolution images made with GANs at the time that it came out, and that was done with a single GPU. And I think that's like a single GPU for the whole paper, not just like a single GPU per experiment, but like they were actually taking turns running experiments on one GPU that all the authors shared. it takes a bit more creativity, but it can be done. Yeah.
So my question also again about the images versus language. So if you look at the images, you go from the like pixel abstraction to the high level abstraction, right? To the cat or dog. So you kind of like narrow your hierarchy, let's say. But in the language, you go many to many. And how would you like imagine? How would you like describe what is going on inside the hidden layers? Like, what are the properties? If we compare them.
Yeah, that's an interesting question. The question is, when you have something like a convolutional net, you start out with pixels and you go to a single high-level description, like this is a cat. And with language, you start with many words, and for a translation system, you end with many words as well. And so what are the hidden units doing? Let me see if I can actually pull something up on the computer here. So Andre, my former colleague at OpenAI, who's now director of autopilot at Tesla, wrote this paper, and I think also you can find like an interactive web demo, if I remember right. Let me see if there's a figure in here that's useful. Yeah, so here he's actually looked at individual cells in an RNN, and he can see kind of what they're doing. So this one at the upper left, it's sensitive to where you are in the line. As you scan from left to right, you go from blue to red. I think blue is active and red is inactive. In the next row down, there's this LSTM cell that turns on when you have quotes, when you're inside of the quotes. That's because when you're generating the text, you need to know whether you ought to close a quote or not. So when you see an open quote, you have this cell that turns on and remains on until you remember to write a close quote. For code, there's cells that activate for if statements and so on, cells that activate for comments. So you can kind of think of them as being a little bit like flags that keep track of your state while you're generating a sentence. He did also find a lot of cells that were hard to interpret, and he shows you how just looking at the output, you can't necessarily tell what this is doing. This reminds me a little bit of trying to understand DNA, that there were a lot of features of DNA where for a long time people thought that they were just garbage, and then it turned out later that there's all kinds of different ways that DNA can be transcribed into RNA and then spliced and recombined in different ways. So things that look like garbage at the start might just be things that are more complicated than we know how to understand yet. And a more sophisticated way of analyzing the LSTM states could tell us something about what this is doing that isn't obvious to us as human observers. It also might just be totally random. Like not every cell necessarily matters. Yeah.
So you mentioned reduced precision, I think in two different contexts. One was for like compressing a model, and then another was for regularization. But I wanted to make sure I understood that regularization would be useful, particularly for weights during training, but you would still want increased precision of your input when you're in like forward or execution mode. Is that right?
Yeah. Let me clarify one thing. There's precision in terms of how many bits do you actually physically allocate to a computation, and there's precision as in how reliable is the actual output value that you get. So like you might have an ALU that can give you an answer in 32 bits, but a lot of them might be random. Does that make sense? So there's a difference between like how many places of precision you have versus like what's the actual effective precision in terms of how accurate they are. So when I was talking about ASICs and how they're faster by having less precision, I mostly meant the answers they give you are a little bit randomized. And then in other contexts, some other people have asked questions about how can you speed up a model or make it use less memory by just having fewer bits that you actually communicate. I'm not sure which of those you were asking about more.
Well,
I think the second of those, but then also you mentioned it as a regularization technique during training using lower precision.
I see. Okay, so the question is, using fewer bits a regularization technique? The thing that I remember saying, what I was trying to mean was that if your computations are kind of noisy, then that's a good regularizer. I don't know of any work showing that just using fewer physical bits at each step is a strong regularizer. It might be, but I don't remember having read that anywhere.
Gotcha. And would any number structure other than like standardized float ever be useful?
Yeah, okay, so the next question is, would any number structure other than standardized float ever be useful? So yeah, people use fixed point arithmetic a lot. Fixed point arithmetic can still handle decimal point values, it's just that the position of the decimal point doesn't move around. There's also a lot of different relatively exotic academic ideas for how to replace the IEEE floating point standards. There's things that are called like posits and things like that. I don't know as much about those. My impression is that a lot of them are valid as an idea, but maybe not necessarily easy to put into hardware. Like a lot of these ideas for how to replace floats rely on the idea that it's easy to implement a lookup table. And my understanding is that with some of the newer hardware, it's not necessarily easy to implement a lookup table as your method of implementing a particular arithmetic operation in hardware. But I don't actually know a lot about any particular proposal for replacing floats or exactly which hardware barrier is relevant to enacting that proposal. But yeah, it definitely seems like something that could be possible, especially because though just speaking at the level of intuition and not as a level of actually having any formal training on this, we spend a lot of time really intentionally restricting the range of values that we use for deep learning, and the floats are designed to handle a very wide range of values. So if we could leverage the fact that the algorithm is only going to use a small number of those values anyway, it seems like we have opportunity for better efficiency there.
I read some examples using CNNs as autoencoders instead of just classifiers, and I was wondering what is that, and what is the CNN working as autoencoder, and what are some practical applications of autoencoders?
Yeah, so the question is, there's some papers about using CNNs as autoencoders, and how does that work? What are some of the practical applications? The basic idea is usually we use a CNN that looks at an image and produces just one output value telling you what's in that image. Like this is a cat, this is a dog. An autoencoder actually looks at an image and outputs an attempt at remembering what that image is. Later in this book, you'll learn about something called variational autoencoders. And so the variational autoencoder is taking this basic idea of an autoencoder and extending it slightly to actually learn the probability distribution over the images. So you can use that to answer questions like, what is the probability of this image occurring in the distribution that generated the training data? And you can use that for things like anomaly detection, like finding images that are unusual, or converting images to be more normal in some way. Like if the image has been damaged, if you have like a photo that somebody scratched, you can imagine like a Photoshop filter that removes the scratches by transitioning to a nearby, more realistic image or higher density image. Another thing you can do with any kind of autoencoder, not just variational autoencoders, is you can use the code that comes out of the image itself. One thing that you can do is you can store your image in a compressed format using just the hidden unit values. And so there's actually, if you've seen the Silicon Valley TV show, there's this imaginary startup called Pied Piper where they're always working on compressing different kinds of data. There's actually startups that do that kind of thing now that are working on using deep learning to compress different kinds of content. It's not necessarily literally autoencoders in the way that you read about them in the simplest form, but it's using some of those same principles of having a deep net that outputs image or video content. And you can also use autoencoders for search. that if you have an image and you want to find other images that are similar, not similar in terms of having the same pixel brightnesses, but similar in terms of the meaning of the image. Like if you want to find all of you have like a picture of a red car parked in a driveway next to a pine tree, and you want to find every other image with that combination of objects and that kind of arrangement next to each other, but you don't really care about, how bright it is or the angle of the camera or so on. Then having an autoencoder that gives you a code describing each image makes it easy to do a nearest neighbor search in code space and find lots of images that resemble the meaning of the image that you started the search with. Some of the first deep learning papers in the latest wave were about this. Jeff Hinton had a paper, I think, in Nature or Science, something like that, about using deep autoencoders to do what today we call semantic hashing, where you map input values to hidden unit points that put similar inputs near each other and different inputs far apart from each other.
There's one more question online. So how can keywords be extracted from product images, like in e-commerce? Is there such work, or would an encoder-decoder strategy be the best way?
Yeah, so the question is, how can keywords be extracted from product images? And I don't actually know a lot about that particular application. My guess is that if you actually have something like photos of text with text on the product, like if you have like a picture of a car and you want to pull out like the brand name of the car and it's actually written on the car somewhere, or if there's like a box with lots of product information on it and you just want to take a picture of it and OCR all that text, you could probably do that with some kind of convolutional network. You might want to have some kind of attention mechanism that has the convolutional network repeatedly visit different pieces of text and zoom in on them. And then you could have some kind of recurrent network decoder for each of the different positions that you run the convolutional net. It's probably a task that's difficult but doable with modern technology. Some things that you might want to read about to get ideas for how to do it are some of the image captioning work that came out in late 2014, 2015. My own paper that I wrote with Yaroslav, who's actually in the audience here, about transcribing address numbers from photos, and probably some of the more recent work about object detection in the different ImageNet challenges, because you'd basically be detecting different areas that you want to transcribe before you run the transcriber.
Any more questions, please?
I saw in the book asynchronous SGD is recommended as the best way of training, and then I saw some recent papers like the big result from Facebook where they train ImageNet in 1 hour over tons of GPUs where they switch back to synchronous. And so is it asynchronous SGD falling out of favor, or?
Yeah, the question is asynchronous SGD falling out of favor relative to synchronous SGD? And it definitely seems like it for the last year or so. I don't follow that area well enough to have a strong long-term prediction. Usually when I go to implement some big distributed training process, I just ask one of my engineer friends what the best thing that she's been using lately is, and just take her advice. But it's one of those things like, on CPU, sometimes it's faster to do fixed point, sometimes it's faster to do floating point. I think partly as the kinds of setups that we have in different data centers changes, that will change whether synchronous or asynchronous is faster. And you can imagine that different kinds of custom hardware are also going to have different properties as to whether it's better to do synchronous or asynchronous. But I've definitely seen a lot more large-scale synchronous SGD in the last year than I did for a few years preceding that.
Is there ever online components to algorithms that use, like, for example, you mentioned some of these large-scale things like Google and Facebook. To your knowledge, are they ever doing like online real-time training, parameter updates in production, or are they generally segregated?
Oh yeah, the question is, how much do we actually do online parameter updates in production? My impression is that that's still relatively rare, and the main reason is that inference is now more or less a relatively working technology. Like running a neural net on a test input is actually pretty reliable at this point. If you've trained the net, evaluated on a big test set, and you have some idea of what it's going to do when you haven't started serving actual requests. Training is still a little bit of black magic that you really need a human in the loop keeping an eye on it, noticing when you start getting lots of not numbers and the cost explodes and so on. It's not really at the point where you can just turn a training process loose in an environment where there's not someone babysitting it and making sure it doesn't go off the rails. There are a lot of applications like fraud detection and like abuse prevention where the people interacting with the system are actually trying to circumvent it, and they keep reacting to the way that the system works to detect their undesired behavior. As far as I know, usually that's the kind of setting where people frequently retrain the model in most cases, rather than the kind of setting where the model actually learns on the fly online.
So like a period nightly or weekly batch or something?
Yeah, like the frequency is going to depend a lot from product team to product team and company to company. But yeah, it's definitely the kind of thing where like you have a person involved in deciding whether to ship the latest version, and there's like a lot of versioning infrastructure going into handling the different systems. It's not like you just have some living, breathing thing constantly updating its parameters and not remembering all of them. But it's always like if you ship something and it doesn't work very well, then you roll it back to the previous time period's checkpoint.
So far in deep learning, I see mostly we use point estimates, but I've been hearing a lot about Bayesian neural networks. Do you think they are going to have big impact soon?
Yeah, the question is, we mostly use point estimates. Are Bayesian methods going to have a big impact soon? I feel like they definitely should. It makes a lot of sense in terms of representing uncertainty better. I think definitely for tasks where there isn't very much data, we could probably see a lot more use of Bayesian methods. For tasks where having an understanding of the level of uncertainty matters a lot. Like for security relevant applications where someone might try to interfere with the system, and it needs to have an idea that it thinks this is the best action, but it's also pretty unsure and thinks maybe someone is trying to fool it. Those are places where I see Bayesian inference having a strong impact. One point pushing back against that a little bit is that in a lot of cases, if you look at the Bayesian posterior for a model with a large data set, the posterior is actually often very highly concentrated. The more data you add, the less uncertainty you have about the parameters. And so in some cases, there's pretty strong evidence that even if you were able to solve the Bayesian inference problem exactly, it would tell you almost the same thing as the point estimate does. And that's part of why we've ended up using point estimates so much, is that there are these ideas that neural nets with weight decay are very close to what you would get if you just do Bayesian inference with a Gaussian prior on the parameters. And clearly that correspondence is less true in cases where there's a lot more intrinsic uncertainty, or in cases where there isn't as much training data to keep reducing the amount of uncertainty in your posterior. But it is one thing to keep in mind. But maybe for the task where you have a billion training examples, we're not going to see a lot of difference from switching to a Bayesian model.
I have a question. Well, now that we're approaching part 3 of the book, and I know you spoke about that in the very, very beginning, like 15 weeks ago when you were here for chapter 1, but maybe you can recap it one more time, like how part 3 is different from part 1 and 2 and what to expect and what's cool about it.
Yeah, so the book is divided into 3 parts. Part 1 was the basic fundamentals of applied math and to some extent some of the computer science ideas that you need to understand everything that follows. I guess part 1 was probably skippable for a lot of you who already knew some of those math basics. Part 2 is really the core of the book, so you've actually finished most of the things that you can just take and go out and use. And part 2 basically describes everything in deep learning that was really, really working as of late 2015 or so. How you can actually build a convnet, build a recurrent net, how you can actually optimize it to solve a task. You can more or less think of part 2 as describing how to do supervised learning. with deep learning. There are a few other topics besides supervised learning in there, but it's mostly supervised learning. Part 3 is getting into research ideas. Basically, ideas that we're not fully succeeding yet as of 2015. You'll see a lot of ideas in there are basically some things we just think don't work that well now, that we have a few more years of hindsight since when we first read it. Some things are ideas that probably could work someday and haven't panned out yet. And you also see a lot of ideas of where deep learning is heading, and in some cases, ideas of where it already has headed. So for example, when you read about GANs in part 3 of the book, they were not very popular yet. And this year, they're one of the most popular topics of research. Basically, part 3 has a lot about generative models and learning the structure of a data set, which is one of the very hot areas of deep learning research. It's also worth mentioning one thing that you're not going to get out of it is deep reinforcement learning. That's something that became very, very popular and influential after we started writing the book. But none of the authors that we got together for the book actually have any reinforcement learning experience, so we don't cover that. You will definitely find the basic ideas behind variational inference, the basic ideas behind importance sampling, the basic ideas behind adversarial machine learning in part 3 of the book.
What work has been done using deep learning to solve combinatorial problems? So either finding exact solutions or approximating solutions.
Yeah, the question is, what work has been done to solve combinatoric problems with deep learning? The main paper that comes to mind immediately is pointer networks. They use an attention mechanism to solve traveling salesperson problems. I think there's been some other things. I think there was a paper about combinatorial optimization from Brain earlier this year, but I don't remember the title of it off the top of my head. Pointer networks? Yeah, like a pointer in C. They use values in the network to refer to specific memory locations that they manipulate. So with the traveling salesperson problem, they can use pointers to keep track of different cities while they're proposing and evaluating different solutions to traveling salesperson.
Cool. Do you have more questions? Good. Thank you so much for coming.
Oh, one last question.
What would be your ideal chapter, section 4?
Oh, my ideal section 4? Well, I guess when we write the second edition, I'd like to either learn enough about deep reinforcement learning to include that myself or recruit a co-author who can write it. Thanks.
Thank you. Thank you.
Is it okay if I ask you this question?
No, I
Okay. When you first published, there was actually a paper that you mentioned, and there was some switching trade-offs between the generator.
Yeah,
There's saving a lot of head space.
Exactly. So where do you see the next two generations of MS4 and like could they be better at building that module,